Welcome, everyone, to the Research to Business Forum. And the intention of this Research to Business Forum is to have some examples of various activities. And then we have a discussion, and basically we're learning more about different topics and how to have research to business and so on. So it's an interactive session with an introductory topic called presentation. So today we have Dr. Yassin Jomni from Zinnova AB in Sweden, and he will talk about malaria detection. So please.
Can you see my screen, by the way?
Yes.
And it's the correct one.
Yeah, I see yellow malaria Zinnova.
Okay, then it's the correct one. Yeah, so my name is Yassin Jomni. I'm the founder of Zinnova AB. Zinnova, I started with Zinnova back in 2016. It was a consultancy company, but now it's more like research consultancy and a lot of stuff. But mostly, so what I do is the money I make doing consultancy, I use them to finance my research. So that way I can be an independent researcher. The last couple of years I've been working with malaria and computer vision models, how to detect malaria parasites in blood smears, both thick and thin, but mostly thick since it's the, but I'll go into that later. So I'll make a short presentation of the disease first, and then I'll go into different diagnostic methods, and then I'll talk a little bit about what I'm doing. So right now I'm doing the computer vision algorithm for malaria detection, and then the future, what we would like to do, what I would like to do in what's the continuation of this, and it would be an automated intelligent fluorescent microscope, but I'll go into that later. So if you start with the disease presentation, so malaria, there are 241 million cases of malaria as of 2020, 627,000 deaths, roughly 1 or 40% of world population is at risk. 95% of the cases are in Africa, and then 96% of deaths are also in Africa. Children under 5 account for 80% of the deaths. And if you think that we in Europe are off the hook, then it's not that case. If you see the map of 2011 and then the map of the 1900s. So in the 1900s, basically the entire world had malaria, and that could, with climate change and how we fly and all of that, that could come back, so to speak. So we really need to do something about it. So now I'll discuss briefly different diagnostic methods that are used today to diagnostic malaria. The most common one is PCR tests. Maybe there are tons of there are a lot of PCR tests. It's a little bit like the COVID test that you buy in the pharmacy. So they're the most common one. They are cheap, but they are very unreliable, and the reliability it differs from brand to brand, but generally they're not so reliable. And then you have fluorescent microscopy. this is fluorescent microscopy is the best. It gives the most accurate results. But the drawback, it's the equipment is expensive, so it's not affordable, usually in Africa. Fluorescent microscopy works in a way that you take a drop of blood and you mix it with a substance, and that substance reacts with the DNA of the parasite. So when you put some excitation light on that mixture, the reactant will fluorescent and emit a light that is apple green in the picture. So you know that where you have the apple green light, there is malaria DNA. So that's why it's so accurate, because it reacts on that. But unfortunately, it's expensive. So the next one is thick blood smears. It takes 20 minutes for a trained personnel to make a diagnosis, and then it's but it's the golden standard according to WHO, and everybody or most of the hospitals use this as so what you do with this is you take a drop of blood, and then you mix it with a substance with a stain called giemsa, and this stain will color the nucleus of everything in the blood. And the only two things that have nucleus in the blood is the white blood cells, which is the large circles in this, the large dots in the picture. That's white blood cells. And then the parasites also have nucleus, so they will also get tainted. But the parasites are very small, so you cannot see them in this picture. You need to zoom in. So the red blood sample, the red blood cells do not have nucleus, so they don't get tainted. So that's why you cannot see them. But this is the golden standard for malaria detection. So the next one is thin blood smears. It uses the same stain, which the giemsa one, the same stain on the thick blood smear, but the blood sample is prepared in another way. So you see here, it's more like whole cells. So, but this kind of detection is not used widely, because with this one you can know what parasite species it is. So you have 4 malaria parasite species: falciparum, vivas, malaria, and oval. And then you can also know what parasite stage the parasite is in. And it's also 4 stages. It's ring, trophozoid, schizont, and gametocyte. So, but this method is not used very often. Usually it's research labs and stuff that use this method because, as I said, I mean, the main gain of this method is if you want to know the parasite species and the parasite stage. But usually the parasite species, I mean, it doesn't differ that much. In a country, you know what kind of parasites you have, what species they have. So it doesn't change that often. So if you suspect that there is a new species coming into your to the country, then you can do this kind of tests. For the parasite stages, I mean, if you just want to diagnose malaria and give the correct medicine, you only need what species it is, and so you don't need to the parasite stage either. So that's why this method is not widely used or only in research labs. So this was those are the 4 most common ways to detect malaria. So now I'll present my work and what I'm working on right now, or this couple 2 years, is computer vision algorithms for detecting malaria parasites in thick blood smears, since it's the golden standard. This computer vision algorithm is divided in two stages. The first one is does some instance segmentation of the picture. So it just analyzes the pictures and then extracts the artifacts in the pictures, and that's everything that is not background, basically. And then you have the next stage that takes those artifacts and classifies them as parasite, white blood cell, or like a stain, or or stain. So, and this this algorithm is currently implemented in a mobile application. So it doesn't take a lot of time to. It doesn't not take a lot of resources to compute, so to speak. So the pros of this is that this algorithm is offline, so you don't need infrastructure, because if you use this like in remote villages, you don't have any infrastructures. So, and it takes 10 to 15 seconds to analyze an image. If you recall, a couple of slides back, it was 20 minutes for a trained personnel to analyze one film, one sample, so to speak. So it's a tremendous gain of speed. And then you don't need any medical expertise either, because the algorithm does the job, so to speak. So the cons of this is different people prepare these samples in different ways. So the variation between the images is kind of huge, so to speak. And then in some parts they use contaminated water, or water that is not so clean. So you have a lot of other like microbes showing up in the preparation, which might give some false positives. So this is what I have been working on for the couple 2 years. Here are some numbers. The algorithm has an accuracy of 91%, and then so humans, I mean, if you have the personnel that does this usually have an accuracy between 50% and 95%. It depends on which country it is and the degree of education and all of that. So according to the WHO, everything above 90% is they have like 4 levels of classification for the personnel, and everything above 90% is level 1. So it's good performance. But of course it could be improved. The only thing I need is more data. So this now I'll talk about the future, what I think the next step is in this project, and that's would be making an automated intelligent fluorescent microscope, the expensive stuff. But my idea is that if one could make a cheap or affordable 3D microscope, because the biggest problem for example, in Africa and all of that, is that there is not enough money, or the financing is not very good. So it should be cheap. It could be 3D printed and then assembled by, and then the stuff that you cannot 3D print, you just order, and then anyone could put it together. It shouldn't be very hard to put together. The idea is that this device will have like a chip with the correct concentration of the reactant, because one of the problems is that people are not so, I mean, they prepare the samples with in different ways. So with that, if we have like the same the correct concentration, we will solve that problem. And then you just put in you put a drop of blood in the chip together with the reactant, and then you just put it in the device. The device will automatically scan the sample, and then you have a screen with and some artificial intelligence that will detect the parasites and then make a diagnosis. So this device should be easily extended to handle other neglected diseases. I mean, it should be like an open device, so you can put your own algorithms or whatever, or change diodes or filters, so you get another kind of fluorescence, or you can remove, I mean, change the LEDs and then remove the filter, so you get like a regular microscope. So it would be, I think it would be a good thing. So this is what I had to say. Thank you for listening. So,
yeah, thank you very much.
I have the app also, if you want to see it in an emulator. Do we have time? Do you still have time, Mikael?
Yeah, it's plenty of time.
Okay. So as you can see in the emulator, the phone is in what's it called? Flight mode. so no internet connection. So you put the phone on an adapter first, and then when you then you take a picture. This is the picture, and then you click on this. It gets analyzed, and then you can save it like this. So now Donald Duck apparently is. This is a demo. I don't have a microscope or anything. So, and then you can zoom in. You can see. This is harder in the emulator than in, because normally, so you see those red things, that's white blood cells, and then the small red circles, that's the parasites. So in this one, it's not that many. So and then you can toggle about which one. The green one is just for debugging purpose, because to see the artifacts that are classified as non-parasites. So you can, for example, in this one, so those are the parasites. So this is how it works. And then if you can also edit, like if this one, you can edit it or remove it. You can, depending if it's not correctly classified. So you can change that. So yes, this is what I had to.
So you've developed that app yourself, yeah?
Yeah, I did everything myself.
Okay. Are there any other apps similar to yours on the market or?
Not products. There are some research institutes that have similar things, but not in the same stage, so to speak, because this app is currently tested in Nigeria, so they're using it in the lab right now. So it's basically almost ready. I need to work on the algorithm itself, but everything else is I need to. There are some few issues I need to solve. When those issues are solved, it could be a product.
So at the moment, the results, the data that you're obtaining and the work that you're doing, what are you doing with that? Are you publishing stuff or you're keeping it sort of secretive or working with some?
Right. I'm thinking of publishing. I haven't done it yet because we had I wasn't sure if I will take like a patent and stuff like that. So if I want to take a patent, I need to take the patent first and then publish later. So, and then I didn't have the financing to check if it's patentable. But I had help with an association called ALMI in Sweden. They invest in companies and stuff like that. So they financed the what you call it, the patentability of both ideas, actually, the phone app and then the microscope, the fluorescent microscope. So the mobile app by itself is not patentable, but if I do some because one of my ideas also is to do like a cheap clamp-on microscope to put it on the app on the mobile phone, so you have like the whole thing. Yeah. So if I have both of them, then I can take a patent. The fluorescent.
The app, the smartphone app is not patentable.
No, because there are some. I mean, even though there is no product, there are patents that are quite not exactly very similar, but what they say is that I have the freedom to operate, so I can use this. I can make a product out of it. So because it's different from the patents that exist. So, but I cannot patent it by itself, sort of, because it's software and stuff like that. So that's why. So my
obviously, being an independent researcher, what will be good for you is to go for the patent rather than trying to go for publication or something, and get the work published.
Yeah, no, but I think if I go that way, I think the fluorescent microscope is a better bet, actually, because that one is the way I thought about it is kind of unique. So, but it's a much larger project as well. So it needs. I can do most of the stuff, but it will take me like more than a year. That's for sure, because it's a lot of engineering, and then you need to comply to standards, which is actually the most that will take most time, so to speak. So, but in the medical field, I mean, you have like the CE how to call it, CE-märkning, the CE regulation. And then you have the FDA in the US, and I think in Great Britain they have like CA now. They used to have the CE, but and to get this certification is very costly, and it takes a long time. So, but the thing is, since this product will be sold in Africa, mainly in Africa, so maybe I don't need to do that. So, but it's still, yeah. But the patent thing, I think, I mean, it depends. In my opinion, it's not only, it depends how you see it, because if you take the patent, you will publish your results. And the thing with algorithms is that you could do things in many, many different ways. So you can take that algorithm, change it a little bit, so you get similar result, but you have like, you have bypassed the patent, and you're using like 90% of the algorithm. So in my opinion, even though, I mean, patenting is not such a good protection against for algorithm as it is for other products, like real products. So I'm not sure if it's the good way to go. So, but yeah, but I think it's more. So, yeah.
And let me ask, because you made your PhD in not in malaria, it was in precision of data, or what was it, something like that, which is industry production or something related.
Industrial electronics.
Yes. And that has been of use, but how did you come into the topic of malaria, that you decided to focus on this?
Actually, it was by accident. I was trying to find like a side project, a project on the side, and then I was browsing the internet, and I saw a picture of like malaria and stuff like that, and I thought, well, I probably could make an algorithm during the weekend for this, but it took me longer than that. But I mean, I started like that, so it was more by an accident, and then sometimes when you get like bitten by something, you don't, I mean, yeah, you just continue. But it has nothing to do with my PhD or all of, but I have worked with image processing and computer. I work with in the automotive industry with that. I mean, with computer vision and embedded system in general. So, but my PhD was in industrial electronics, and it was more, not that much electronics actually. It was more like physics, heat transfer. It was about measurement accuracy in district heating substations. So it was a lot of like heat transfer modeling and stuff like that. And then also actually to some extent algorithm, find better algorithms to measure heat energy. So it's like a totally different, but my whole career has been like that. So,
Yes.
What was your first degree before PhD?
Engineering physics and applied mathematics. That was my first degree. And then I changed to electronics for my PhD. And then when I was done with my PhD, it was more like programming and embedded system development. So, and then algorithm design, and then like computer vision.
So you're also kind of a coder as well, aren't you? You do coding.
Sorry?
Coding, computer coding.
Yeah, but I'm more into like smaller smaller devices, like you know, the electronics that you find in cars, or such stuff, like embedded systems, or in your fridge, or so it's more boring kind of coding. It's more like hardware. Yeah, it's another. And with my last, and then I've been consulting in that area, so to speak. So my last in my last I was working with in automotive. So I was working with image processing, algorithm development, embedded development, and then also like cybersecurity, all of that stuff for small devices, so to speak.
I think this is a nice example that we start with something and then we gain experiences, and then we can actually shift to other avenues where it was not, where we are not really experts, like malaria and the disease stuff and medical, but we can make a contribution and it can create something unique. So also like young people, they are usually so focused on the career and everything must be perfect and all those things. But many things in life are not perfect, but then we will shift along the way and get other interests, and we meet other people and so on. And basically, if we would be able to shift along with our own motivations and things, then we would be happier, and we will actually think more about the work. So instead of having the career which is safe regarding employment or things like that, but maybe not as exciting, then this is it shows that it is possible to do it in some way. And then of course nothing is 100%, so you only have money for this, so you need to go and do consultancy things and spend this intense number of periods for collecting the money, and then you use it or so on. But if you would give this example to some young people, or like Nasar's son, for example, when he start to think about these things, then he will also get ideas, like he already got about the coding camps and so on, and YouTube sending, which he has seen you doing. Then we can inspire the young people to actually take steps towards things they are interested in, and still in, maybe when they are in the decision mode, they will see that, oh, I saw this presentation by Yassin Jomni. He made it, malaria. So then they will choose the path where they have more happiness.
Yeah, actually, it's for me. It's I don't think I will take a regular job. I mean, it depends what kind of job, but I would be really picky, because it's as I see it, the most important thing is you do the stuff that you like. So if you label them like research or something else, or development, or it's not important. I mean you do the stuff that you like, and then don't bother a lot about the labeling of that, if it's so. And then also I want to say something. You have, usually if you, if you're at university, or knowledge is like a pyramid. So to get that really, the sharp knowledge, spjutspets, how do you say that?
Spearhead.
the spearhead knowledge, I mean the really, really expert knowledge, you need like a large base. So with that base, actually, you can do a lot of stuff. So you can do, so you can apply a lot of knowledge to other fields as well. So even though you don't work with your spearhead knowledge, you have a huge base that you can, I mean, work with and make nice contribution. For example, image processing or like computer vision in malaria. And I think there are a lot of like synergies one can have from different area of research as well. I mean, you can take like, I've been to seminars about computer, new like AI research, and that I could apply for the malaria project. So it's like a nice synergy. I'm not sure if it will work or not, but it's new ideas that could be tested at least. So
yes, these new ideas, they only come from meeting new people and new inspiration. And when I talk about creating new things, then we should meet other disciplines. In the beginning, it's so difficult to discuss because we are talking different languages, sort of. But after a few rounds, we know more, and then there will be some ideas which emerge thanks to the difference what we are doing. So that's when our base of knowledge where we are interested can come into new use, which is revolutionary in the best case. And like now, when you come into this new avenue, you got excited one weekend and you were thinking half an hour would be enough, or half day to solve this, but it took longer. But if you solve the malaria detection, then it's a lot of lives which are influenced by this. So this is a nice contribution.
Yeah, actually, the first model I made was for thin smears. You know, the one that is not that used only. And then I came in contact with the malaria professor in Sweden, in Stockholm. And then he said, well, that's not, usually you don't, that's not used that often in the field. Usually people use this, I mean, the thick smear. So I started working on that as well. So it's like a continuous thing.
Yes.
So.
How is the community here? Because you are active and so on, and we can maybe finish sort of temporary milestone because NASA will be leaving. So then you and I can continue some more discussion. So what is your reflection, NASA?
Yes, I think it's amazing. You know, I didn't know much about this malaria thing and the work that Yassin is doing and these apps, and I think it's very, very new. And it's interesting that he mentions that to do something that they enjoy and not worry about how it's labeled. And that's absolutely true, because I think if you're passionate, you know, if you have a passion for something, and if he wants to see a result of this malaria thing, which is affecting not just in Africa, but other parts of the world as well, you need to have that passion, because that passion will actually stimulate innovation. Yeah. When you're very passionate about something, you're more likely to come up with some innovative steps, and you'll be doing more innovation in that. Yeah. So I think it's good that what he's doing. You know, he just needs to keep going. And work with others as well. Yes, working with other people, and I'm sure it'll do well. You know, and whether you get a patent but you know, you'll be successful in that. The app looks good. Everything is now turning app now. It's all app based, and you know, there's a lot of science behind it that's involved. And if you can sort of do all that, I think the world will benefit, especially the African countries, which malaria is affecting mostly. So
Yes.
I think it's good work.
Yeah. And also we can maybe we can have this inspirational presentation also to the young professional society and the young people there. So that's an idea.
Absolutely, yes, absolutely.
And then
Oh.
I'm happy to collaborate as well. If you have ideas and stuff, maybe it will be something. And I think I have you on LinkedIn.
Yes,
as well,
I think so.
Yeah.
Maybe you send your company website and that. So
The website is, I mean, you see this thing. Sorry, that one.
yeah,
The QR code. So if you
I was trying to go on that code.
But the company. But the company website is under construction. It's very messy right now.
Yes.
I have changed. Yeah, exactly. It's not. It's
okay. Well, it's working. Then the young people, they will use
Yeah,
this,
yes.
and we can find out. So it's a good test. Okay, then thank you very much for attending, Nazar, and
Okay,
I will continue discussion with Yassin. So see you later. Okay, thank you very much, and let's wrap this up, this forum, so it becomes.
Finns det fler eller? Är det bara du och jag?
Det är bara du och jag, men vi kan avsluta på engelska så blir det en hel film eller avsnitt.
Jag glömde.
So in summary, what we have here is a nice example of independent research where you do something from your background, and we don't need to be at a big university and traditional profile and build up and so on. So there are things where we can contribute in our own ways. So this is what you have created here, and then in order to come to the next level, maybe we can use our networks and so on to trigger, and this is part of the visibility through this forum presentation and discussion and so on. So that's my thinking.
Thank you.
Okay, so then thank you for this presentation.
Thank you for having me.